Okay, good afternoon. Howdy.
Howdy. Hope you guys had a good weekend. It's time to get started with the lecture for today. But before we start with the lecture, there's a couple of things that we need to address. First, there's a homework that is due on Wednesday. I posted the homework on Thursday. So just make sure that you go over the homework. You have to submit the homework on Wednesday. I think you only have to submit 5 problems. If you don't have the textbook, I made the copies, and also the problems are also in the tracks system. So you can get access to the book notes as well. And something else that I did was to post a note for Wednesday. So if you were not able to get all the notes or write all the notes in class, you should be able to access the new slide with the notes. Okay? Any questions? So basically what we did last time was to start discussing the material on joint probability distributions, and started by basically going through the set of topics that we had covered in class, from sample space up to probability distributions for discrete and continuous, and the joint probability distribution for both cases. Okay, so that was the last thing we did. Something else before I forget. If you haven't got your exam back yet, I brought the exams with me. So if you want to get your exam, I have the copy with me, so you can come talk to me at the end of the lecture. So joint probability distribution. Just really quick, let me go through what we did last time. So we covered the concept of joint probabilities for the discrete case and also for the continuous case. We went through some examples. This particular example was for the discrete case. For the continuous case, we define the joint or joint density probability distribution as the double integral for the area A. So for the discrete case, you look at the summation of both variables. For the continuous case, you look at the integral. Okay? So it's a double integral. So here's the formal definition. We went through this on Wednesday. We worked on this example. And also then we cover what a marginal distribution is. Again, for the discrete case and also for continuous. And this is the last example we discussed in class. And basically, I think the last thing I tried to do was to substitute these numbers into this expression. And we noticed that when you substitute 1 here, you get a probability that is higher than 1. Remember that? Does anyone know why is that happening? I mean, the numbers and the functions are okay. There's no error. So remember, we're looking at continuous joint density distributions. So when you look at the probability, it's not like you can substitute the number and get the probability. You have to look at the integral. Right? So in order to get the right probability, so this is not correct. So if you want to get the probability for 1, you actually have to go from 0 to 1, the integral of this expression for x. Okay? Is that clear? So remember, this case we are looking at continuous. So you're looking at the probability just for x. So you need to integrate with respect to x. In this case, I'm looking at the probability of from 0 to 1. So that should give you the integration of those intervals should give you the probability. Yes, sir.
On h of y, in our integral is 2/5 times 2x plus 3y. Where did the 2 go?
Here?
We integrated down.
Okay. Any other question?
That's the x or dy.
This one is the x. Okay. So that was the last problem we discussed. So a new material for today starts now. So remember we discussed for just one random variable, we discussed how to get the probability of an expression given something. Now we're going to take that concept to a joint probability distribution. So the value of x of the random variable x represents an event that is a subset of the sample set. So this is something that we've been repeating over and over throughout the semester. If we use the definition of a conditional probability as stated in lecture 5, we remember that if you look at the probability of B given A, you can find that probability looking at the intersection of the two events given the probability of A happening. Okay? Where A and B are now events defined by the probability of x being equal to x and the probability of y being equal to y. So now we are looking at the two different random variables, and we want to find what is the probability of those two events happening when we know something already for one of those random variables. So if you look at the probability of y being equal to y given that x is equal to x, then you can find that expression or that probability using this expression, which equals to the function or density function for the joint distribution, x and y, given the marginal distribution of x. Remember, g of x is the marginal distribution of x. Okay, and we study how to get that marginal distribution from the joint. Okay, so you can use this given probability given of an event concept when you have a joint probability distribution. Okay, so the formal definition, if you have two random variables, x and y, discrete or continuous, the conditional distribution of the random variable y given x equals x is given by this expression, which is the density function of y given x, and that probability you can find using the joint distribution of x and y given the marginal distribution of x. Same thing for x given y. The only thing that changes now is that instead of having x given, you have y, and you use the marginal distribution of y. Okay, so this is a concept that we already know. We have extended that concept to the joint probability distribution. Okay, so if we wish to find the probability that the discrete random variable x falls between a and b, when it is known that the discrete variable y equals y, we evaluate that. Remember, this is a discrete random variable. So we look at the probability of x being within that interval, given that y equals a particular number, let's say 3. Okay? So in order to get that, in the discrete case, you look at the summation for the interval using the density function of x given y. So we can extend this case also to the continuous distribution. So for the continuous case, instead of looking at the summation, we look at the interval. Okay? So again, these are the concepts that we learned for just one random variable. What we're trying to do now is to extend those concepts when you have a joint density distribution. So let's look at this problem or example. So here we have the joint density function that is given by for a random variable x and y, where x is the unit temperature change, and y is the proportion of spectrum shift that a certain atomic particle produces. And we have that joint density function, which is equal to 10x times y squared for the interval between 0 and 1, and we know that x is less than 1. Okay, so the first question is find the marginal densities for x and y, and the conditional density f given y given x. Okay, so let's review how to get the marginal distributions, the marginal densities for x. So this is from Wednesday. We know that g of x should be equal to the integral from minus infinity to infinity of the function, the joint density function, with respect to x or y? Y. Okay? So if we solve this, our limits are going with respect to y. So we look at y here, and we know that y goes from x to 1. So this goes from x to 1. And our joint density function is 10xy squared with respect to y. So if you integrate for y, you have 10 over 3 xy to the power of 3 when y equals 1 and y equals x. And if you solve this, you should get 10 over 3 x times 1 minus x cubed. And this is for x between 0 and 1. Okay, so this is the marginal distribution for x using the joint distribution for the problem. Now we need to find the marginal for y, which is essentially the same process, but instead of doing an integral, just state the integral here, x, y, with respect to x. So this integral is going to go from where? 0 to y. Everybody knows why? Because x goes from 0 to y. Okay? So state the integral, x y squared dx, and that should be equal to 5y to the 4th when y is within 0 and 1. Okay, so now we need to find f of y given x, which is the third part. So in order to find that, we know that this expression equals f of x and y given g of x, right? Well, we know that by definition. So the only thing you have to do is to substitute the function of the joint probability distribution, which is 10xy squared, divided by the marginal of x. This should be over 3. 1 minus x cubed. And if you solve this, you will get that this equals 3y to the power of 2, 1 minus x cubed. And this is for 0 less than x less than y less than 1. Okay? So now we have the probability of y given x. Part B is asking, find the probability that the spectrum shifts more than half of the total observations, given that the temperature is increased by 0.25 units. So from the original description of the problem, we know that y is the proportion and x is the temperature. So if we want to find the probability of that happening, can I move to the next slide? Yep. Let's set up the expression. So what we are looking at is at the following. The probability of y be greater than 1/2, given that x equals 0.25. Okay, so find the probability that the expression will shift more than half of the total observations. This is given by y, given that the temperature is increased by 0.25 units, which is x. So the expression is right here, probability of y being greater than 1/2, given that x equals 0.25. So knowing this, we can integrate from 1/2 to 1 f of y, given that x equals 0.25 dy, and that will be equal to 1/2 3y squared 1 minus, we know the value of x, right? So we can substitute that number, 0.25 cubed dy, and if you solve that expression, you will get 8/9. Okay, so we know the expression right here. Now we know that x is going to be equal to 0.25, so we can substitute that number here and get this expression. And when you solve and integrate with respect to y, you get the probability of y being greater than 1/2, given that x equals 0.25. Okay, so that's one of the examples. I have another example here, and I want you to work on this one on your own. So I'll give you 5 minutes. Let me go to the next slide. It is essentially what we just did. I wanted you to get some practice. So try to work on this, and we're going to discuss it in 5 minutes. And you need to evaluate this probability of this. just wanted to let you know, I just found out, I was looking at the grades of the exams and also at the grades of the quizzes and the labs that we do in class. And there's a relation, straight direct relation between the grades of the people who do well in the lab and also the people who did very well in the exam. So if you try to work on the examples in class and try to understand the material, it looks like it helps to do well in the exam. Anyone has the value for the marginal of x? X over 2? And the marginal of 1? Correct. So it's 1 plus 3y squared over 2. So this is g of x, and this is h of y. So those are the marginal distributions. Now we need to find f of x given y. So the conditional density f of x given y so we know the joint density is given, so that's x times 1 plus 3y squared divided by 4, and all this divided by 1 plus 3y squared divided by 2. So as you notice, this cancels, so you get x over 2. Any idea of why this happened? This is equal to the marginal of x. Kind of. So the question is, you look at the marginal for x, look at the marginal of y, and when you look at the conditional probability, you get the marginal of x. Correct. Yes. So they're independent. So one of them, they don't have any contribution, or they don't affect the outcome of the other. Okay, so is that clear? So the conditional density, it means that it's equal to the marginal of x, so they are independent, but we still can find the probability of this event right here. So that probability is x 1/2, y equals 1/3. So that will be equal to from 1/4 to 1/2 x over 2 dx, and that equals 3/64. Okay? So again, knowing something about y does not affect the actual outcome. Okay? Because y has no effect on variable x. That's what this problem is showing. Any questions? So, statistical independence, if the probability of x given x, y does not depend on y, at least in the case of the example we just saw, then this probability f of x given y is going to be equal to one of the marginal, and also be equal to the multiplication of, and the joint distribution is going to be equal to the multiplication of the marginal. Okay? So if y has no impact on the outcome of the random variable x, we say that y and x are independent random variables. Okay? So they are independent. And here, the showing is the formal definition for a statistically independent random variable. So the joint distribution is going to be equal to the multiplication of the marginal. So if you know the marginal of x is the marginal of y, and you want to know what's the joint distribution, you just have to multiply them if they are independent.
So if we restate that first line, doesn't matter. Y is not dependent on x because whatever given x is y.
Because let's look at this. Here you're looking at the conditional, so you know something about y, right? But when you look at the actual expression for the conditional distribution, there's no y in it, which means that y has no effect on the probability of x. So that conditional distribution is telling you that y has no effect. So it's just like they're independent. Any other questions? Yes, sir.
Does it go both ways? Like you said that it doesn't depend on y, like x doesn't depend on y, but you say that y doesn't depend on x as well?
Yes, they're independent, so it should be yes. Both of them have y has no effect on x. X has no effect on y. Yes. And any other questions? It goes both ways. Okay? So statistical independence, that's the last concept we cover in this particular lecture. So in this lecture, we talk about random variables and probability distributions, specifically the concept of the random variable. So that was one of the questions of the exam, to know by now what is the random variable. We talk about different distributions, discrete and continuous, and this topic, joint probability distribution, was this lecture. And we look at how one variable affects the other, and also how to get the marginal distribution for a joint probability distribution. Okay? And the last thing we covered was the concept of independence for joint probability distribution. Okay? So this covered the material on random variables and discrete and continuous distributions and joint probability distributions. Now we're going to transition to a new topic, which is in your textbook, is chapter 4. So let me change this.